line. Can you confirm or if you can hear me clearly?
I can hear you.
Okay, thank you so much for confirming that. Okay, so I also need the personal line to confirm if you see my lecture slide. I see my lecture slide.
Yeah, I can see it.
Okay, good morning, everyone. I want to welcome you to another beautiful week. Of course, the focus today will be on logistic regression modus. Um, in the outline, I'm going to walk us through what I call simple binary logistic regression and how do we assess logistic regression model in terms of evaluating the model. Then I'm also going to introduce you to multiple, I think I wanted to say multiple logistic regression. Then we're also going to talk about the likelihood ratio test, then the steps involved in analysis of logistic regression model. Okay, so let's get started. Actually, today, what we've been doing before, we actually been considering relationship between um, the response variable y and independent variable s, and the nature of the response variable uh, up to last week was continuous in nature. But what of in a situation whereby the response variable is categorical? If the response variable is categorical, we cannot use linear regression. So let's look at a categorical response variable. Like take a look at this. Whether or not a person smokes, that's categorical. Okay. So which means the response variable is being categorized into smokers and non-smokers. Maybe what we basically want to do is to look at the effects of some predators on the categorical response. So another example is success of a medical treatment. Okay, in a medical, it is not all patients that could actually gain from medical intervention. You know that, right? Okay, so some they're basically going to survive, and some basically going to end up dying. So the success of a medical treatment can actually be referred to as a categorical variable. Now, in these two situations, the response here is binary. What do I mean by binary? The binary means that we got two possible outcome. Does that make sense? There are two possible outcome. So that is why we actually call that binary. Okay, do you know we can also have a situation where we the nature of the levels in the response variable is going to be more than two. Okay, where you have agree, neutral, disagree. At times maybe you are seeking to investigate the perceptions of your customers, okay, about you know the service you render, okay, and whether they're going to they agree with your service, or the service you render, or whether they don't agree, or whether they actually going to or feel neutral. So in that kind of situation, we're no longer talking about binary, because we got more than two possibility. Now, in this situation, we call this ordinal. Why do we call this ordinal? Ordinal in the sense that the response is ordered. Ordered. We take a look at agree. Okay, you take a look at the neutral, you take a look at disagree. If you basically want to rank that, maybe disagree is 0, okay, and neutral is 1, agree is going to be 2. So in a situation where the levels of the categorical response variable is being ordered, we're actually going to call that ordinal response. Okay, I'm going to walk you through what I call binary logistic regression model. For instance, we have y equal to is a binary response, and we have a predator s that is a quantity t. Okay, now we basically are going to consider a pi, which is a proportion of 1, which is going to be yes successes at any x. The idea here is just like giving any values of x. Okay, let me give you an example here. Somebody apply for student loan. Okay, there are two possible outcomes, right? It's either you are granted or not. Okay, now maybe x is could be your ability to pay. It could be your GPA. You get what I mean? Now, at any value of x, you basically want to figure out what is the proportion of yes success. What is the proportion, like what is the probability that you're actually going to be considered the loan? Okay, or you apply for graduate admission. Okay, it's either you're going to be granted or not. Okay, I know they're going to put into consideration uh certain predator. Okay, like what is the prestige of your undergraduate institution, what is your GPA, what is your GRE, and so on like that. They're basically going to put into consideration so many variables. Okay, now in logistic regression, let me tell you this. I first going to tell you this. Why is it that we cannot use linear regression, okay, in a situation where the response variable is categorical? The reason why we cannot use a linear regression model is because fitting a linear regression model, you're actually going to have a nonsensical prediction that will go over the range of 0, 1. Because when you take a look at the response variable that is categorical, we're actually going to label that as 0, 1. Okay, 0, 1. And if you fit linear regression, okay, the prediction you're actually going to make could be less than 0, and they could be greater than 1. And that doesn't make sense. Okay, and that is the reason why we actually need a brand new model that we ensure that that is not going to go out of bound of 0, 1. And what we're going to do is to apply what I call the log. That means there's going to be a kind of a generalization of linear regression model. Okay, when we generalize linear regression model, we're actually going to have a brand new model that we're going to call logistic regression model. And if you take a look at what you're seeing now, pi, right? Pi is maybe the probability of yes that you're going to be giving graduate admission. 1 minus pi is a probability that you are not going to be giving. Therefore, the ratio of pi to 1 minus pi, that is what we call odd ratio. Odd. Okay, so this guy now is actually called odd ratio. Okay, that's what we call odd ratio. So this guy is going to be the probability of yes. And this guy, okay, is going to be the probability of no. Okay, now the logarithm, the logarithm of the odd ratio will actually restrict, okay, the range of the response to 0, 1. Does that make sense? Okay, the log, the log reading, what we're more or less doing here, we're doing what I call a transformation. You remember the other time when linear regression doesn't work, where I walk you through the logarithmic transformation and so on like that. But for the case of situation where the response variable is categorical, where the range is going to be from 0 to 1, we needed what I call the logarithm of the odd ratio. The logarithm of the odd ratio will be linearly related to the predator X. Does that make sense? Okay, so this is logic form of a logistic regression model. We also have a probability form. Now, what you see at the other hand, that's a probability form. And let me tell you this. Do you know from the logic form, you can actually figure out the probability form by solving for pi? Does that make sense? When you solve for pi, I need those of you online to confirm again if you are still hearing me clearly.
I can still hear
Again.
you.
Okay, thank you so much. Thank you for confirming that. Okay, so like I said, from the logic, okay, from the log of pi divided by 1 minus pi, okay, equal beta naught plus beta 1s, okay, the moment you solve, okay, when you solve for pi, okay, when you solve for pi in this equation, okay, when you try to solve for pi, you're basically going to have, okay, exponential raised to power that, okay, okay, because this is a natural log, okay. Now when you solve for pi, you're actually going to arrive at the probability form. Does that make sense? Okay, so these are the two kind of, you know um the logistic regression form that we have. We got a logic form and we got a probability form. Okay, so don't forget, that log. I said it's not just a log, but it's a natural log. Okay, so the next thing I want to do now, okay, you have data set, right? How do you actually implement that in R? Okay, I have a data set where I'm looking at the effect of height on gender. Of course, my gender is what? Gender is categorical, right? Either male or female. Okay. Now, what I want to figure out here is if I know the height of somebody that I've not seen, okay, is the height enough for me to make a prediction of whether the person is going to be male or female? What are we doing here? This is basically going to be a classification problem. Does that make sense? Now, this is a coding out. Okay, the coding out, I'm going to tell you now the difference between how we code logistic regression and how we code linear regression. Uh, of course, in the logistic regression, you're going to put a GLM because it's a family of a generalized linear model. In the case of logistic regression, sorry, in the case of linear regression, you put LM. And not only that, you're also going to indicate family equal binomial because the underlying distribution of the response variable is binomial distribution. Does that make sense? So you're always going to indicate that. And the data set that I'm actually using here is sparse. And when I actually run that summary, this is what I'm going to have as a result. Now, if you take a look at this result now, it's looking like that of the linear regression output, except that there is something that I needed to pay attention to. In the case of simple linear regression model, where you see a z value, what do you normally see? T value. Does that make sense? And in the P, when you see PRO, parentheses greater than the absolute value of Z right now, what you're going to see in the case of linear regression, basically going to be T. So which means in the case of linear regression, we make use of t-test. You get what I mean, right? Like if I want to figure out what is the significance of a particular regression parameter, but here is basically going to be word statistics. We call it word. Okay, the word. We call it the word. Okay, we call it the word test. Okay, which we actually denoted as a Z. Okay, now let's take a look at the output right now. Now looking at the output that we got, okay, I needed to pay attention to the estimate. Okay, now in the output, take a look at that estimate, right? In the logistic regression, we're actually going to call them, look at the name. We're going to call them, the name we're going to call them is actually log odd estimate. We call them log odd estimate. Please take notes. We don't just call them estimates. Okay, we actually call them log odd estimates. They are not just estimate, they are log odd estimate. Please don't forget that. Okay, now if I want to write the fitted model now based on what I have, okay, based on what I have, if I want to write a fitted model now, I'm actually going to write that. Take a look at that. You remember the other time in probability form, okay, this is what I'm actually using. I'm going to go back to what when I specified that the other time. Do you see that? What am I just plugging in the probability form? I'm just plugging in the beta node and the beta one, right? Okay, so plugging them in, you're basically going to see now what we're going to have. Okay, so that's what we have. Okay, so it's gonna be pi cap. Don't forget, gonna put a cap. It's an estimate. So that pi cap is the probability. Okay, it's basically gonna be the probability of somebody. Okay, being that I've seen the height, either it's gonna be a male or female. Let me tell you this: if we coded gender, if you coded male as 1 and female as 0, okay, that very pi is the probability of somebody being a male. Does that make sense? Coding male as 1 and female as 0 does not mean uh, the one I coded as 1 is actually going to have a numerical advantage. That doesn't mean that. You get what I mean? So I can as well code female as 1 and code male as 0, but for interpretation's sake, okay, for interpretation's sake, when I code male as 1, okay, when I code, okay, let's say this is what I do. If I code male, okay, as 1 and I code female, okay, as 0, okay, if I code male as 1 and female as 0, that very pi cap that we are seeing right now is the probability of being a male. Okay, is the probability of being a male. When I plug in height, when I'm giving an individual, okay, of a particular height, and I plug in the value into the expression and I subtract, okay, whatever that I compute is basically going to be the probability of being a male. Okay, now if what I got is 0.8, I'm just assuming, then it means that person is more likely to be a male than being female. And if the probability is a 0.2, okay, if the probability is a 0.2, then it means that person is not more likely to be a male. If it is not more likely to be a male, then it's basically more likely to be female. Does that make sense? Okay, that is exactly what we mean. Okay, now like I said, but in this situation, our pi cap represent the proportion of females. Now, if I'm taking proportion of female, then it means I'm assuming I coded female as 1 and I coded male as 0. Based on what I said now, based on I'm saying that pi cap represent the proportion of females at that HGT. So which means, okay, what I have in my numerator is actually I was initially considering female. Okay, I was initially considering the probability of female divided by probability of male, and this is what actually what I'm considering. Okay, so the ratio of that, so the log of all of these, okay, is what is basically equal to b1 x1 height. Does that make sense? Okay, so which means what I have in my numerator is actually female. That was why I'm saying that represent the proportion of female. Okay, the characteristics of interest is basically what I have in the numerator. Okay, now does that really make sense now? Okay, now I want to go into how do we assess logistic regression. Okay, now if you want to assess logistic regression, take a look at what I have now. Maybe I'm looking at the effect of GPA, okay, on a particular, you know, response variable. And the response variable is categorical, okay? The response variable here is categorical. Maybe whether the person is going to pass or not, okay? We're looking at the role played by GPA, and this is what we actually have, after running the regression output. You can see the p-value, then you can see odd ratio, right? You see odd ratio 1.73. The odd ratio is when you actually consider the ratio of pi divided by 1 minus pi. This is what we call odd. This is what we call odd ratio. Okay, that's what we mean by odd ratio. The odd ratio is actually 1.73. The fact that if odd ratio is 1, that's 50-50, right? If odd ratio is greater than 1, what does it favor? If a ratio is greater than 1, it favors the numerator, right? It favored the numerator, right? That's why you see 1.73. And what you see at the other hand is a confidence interval, 95% confidence interval for the odd ratio. What we're trying to tell the world, the 1.73 lies, the true value of the odd ratio lying between 1.27 and 2.35. Okay, now if I want to assess, you remember the other time when we are assessing, uh, regression model. Okay, we can assess regression model by testing the how significant is the slope. We can also test that here in the case of logistic regression under the non-hypothesis beta 1 equal to 0, alternative beta 1 not equal to 0. But let me tell you this, in the case of linear regression, we actually use a t-test, right? We got t equal the beta 1 divided by the ratio by the standard error. But right here, what am I saying? I'm writing z instead of a t. Of course, what you have in the table for GPA 10, that very z, what you're calculating is 0.545417 divided by 0.157931. So the result is going to be 3.45. Do you see 3.45? Okay. And if I have that as 3.45, as I'm actually saying here, what is the p-value associated with that? The p-value associated with that is 0.001. And of course, with a p-value less than 0.05 level of significance, we're basically going to reject the non-hypothesis. And we can also construct a confidence interval. That confidence interval that we are seeing now that we've obtained, that is a formula. Beta 1 plus or minus z multiplied by the standard error. Do you see that now? Okay. So that is a formula we basically use. Now take a look at this. Do you know that under the non-hypothesis, if beta 1 equal to 0, you remember the other time when we are also testing the significance of intercept, when you were comparing intercept with a model, you remember that we use f-test, right? You remember the other time? Now, if I actually have a logistic regression model, give me 1 second. Okay, so if I have a logistic regression model, okay, And I actually, the logistic regression model is actually this guy, okay, equal beta naught plus beta 1x. Okay, when beta 1 equal to 0, what do I have? I only have this equal to beta naught. That's what you see now. You see that? In the null hypothesis, when beta 1 equal to 0, then you are trying to say the logit, the log odd, okay, is only related to the intercept. It's not relating to x. But the alternative is going to say, okay, you got a full model, okay? So what I'm trying to showcase you to you now is, situation where you are comparing between an intercept model, okay, in logistic regression model with a model with a predator. You get what I mean? So that's what I mean. Okay, now that's all about the simple logistic, binary logistic. When I say simple binary logistic, you know what that means? The simple binary logistic actually means I am actually considering, a categorical response that have two possible outcome, and I'm only considering one predator. But you know what I want to do now? I want to walk you through a situation where we got more than one predator in logistic regression model. You remember we did the same under linear regression model when I walk you through linear simple linear regression model. From that, I actually extended that to multiple linear regression model where you're actually going to incorporate more covariate. I told you the other time, I work on that in Nigeria when I was working on my capstone project, where I look at the effect of exchange rates, inflation rate, consumer price index on the GDP of Nigeria. But right now, what if in a situation where we got more than one predator variable that can actually be related to to a categorical response. Now, if you take a look at that now, look at the first one. That's a logit form, right? That is a logit form of the multiple logistic regression model. Or what you're going to see that we keep on adding beta 2, x2, beta 3, x3, and so on like that. And in a probability form, you're actually going to have the second model, giving us pi equal to that. Any question? Do you understand that? Do you understand the specification, right? Okay, the person, those of you online, can you say confirm if you see hear me clearly? Those of you online.
Yep.
Yep.
Okay, thank you so much. If there's any question, make sure you ask. So this is a module specification for multiple logistic regression. Now, in a multiple logistic regression, I also want to remind you of this. When we're dealing with linear regression, we actually saw ourselves comparing models, right? We compare simple model with a complicated model. I remember we made use of a nested F test, right? We're also going to do something like that in in logistic regression. Now I needed to take a look at the non-hypothesis here. What is it talking about? Situation where beta 1 equal to beta 2 or equal to beta k equal to 0. What is HO telling you? Intercept model, right? Okay, that is what HO is telling you. When all the slopes is 0, then it means the logic, the log of the odds ratio is just going to be equal to beta naught. And while the alternative is going to say at least 1 is not equal to 0. Now, how do we compare a reduced model with a complicated model in a logistic regression? Is what I want to show you now. Okay, we actually use the idea of a likelihood ratio test. Okay, the likelihood ratio test, and that is why you are seeing that guy now. The G equal -2 log of H0. The H0 is a likelihood function when the non-hypothesis is true. That's why you see that as H0. Okay, the likelihood value when the non-hypothesis is true, and why the other head is when the alternative is true. And that is why we call it likelihood ratio test. It's like comparing two likelihood associated with the non hypothesis and the likelihood associated with the alternative. But you know what? I'm going to walk you through how to implement that in R. Now take a look at what I want to implement now. If you want to implement this in R, where you want to compare complicated model in logistic regression, you want to compare the simpler model with the complicated model. You need to first load. You need to first install a package called LM test. You see LM test, right? Now the data set that I'm actually want to use today is an online. This data is actually online. You can just copy this into R. It's a data set on grades. Okay. Now, the variables in this data set is age, travel time, study time, absence. Okay. Per one grade, per two grade, and the final grade. Okay. Take a look at that. Okay. Now, those are the variables in this data set. Of course, uh, you know, we basically, if you take a look at that now, those are the variables. Now, of course, when you are conducting a likelihood ratio test, in the non-hypothesis, you're going to have a simple model. In the alternative, you're going to have a complicated model. Okay. Another name for complicated, for complicated model, you can say full model. Full. Okay. Another name for simple model. Okay. You can say reduce. Reduce model. Okay. Now, let's consider a simple model. In a simple model, look at the code. We actually want to predict final grade. It's just like I know some of you are anticipating, you're actually curious, like anxious about what your final grade is going to be in this course. You get what I mean? Okay. Now, in this, we're now considering simple logistic regression model where we want to look at the role played by absences. Absences like, when maybe you've not been coming to class regularly, that could impact your grade. Okay. But in the complicated model, okay, look at the complicated model. We actually adding some other variables like not only absences, we also incorporate age. You see that now? We incorporate age. Okay. Now, if I now want to see, and don't forget your response variable is categorical. The final grade is categorical. Maybe you said that you pass or you fail. You get what I mean? Okay, it's categorical, and that is the reason why you are actually fitting logistic regression model. And right now, you basically want to compare. Should I just use simple binary logistic model, or should I use a multiple binary logistic regression model? Okay, so here now we're comparing the simple model with a complicated model. In the case of a linear regression, you remember we normally make use of the nested F test. You remember that, right? The code in R is going to be ANOVA into the two model, but right now it's not going to be ANOVA into the two model. For the case of logistic regression, it's basically going to be LR test. LR test into the nested complex. When I say nested, I'm referring to simple. Does that make sense? Simple, false. Simple is nested. Then when I say complex, I mean complicated. Does that make sense? So if you want to write that, instead, you can just write LR, okay, test into simple, complicated. Does that make sense? Because you define the first one as simple, the second one as complicated. Make sure you write simple first before the complicated. Can we look at the result? Oh my God, this is the output. Take a look at the output right now. The non-hypothesis we support the simple model, just like the same way we have in a linear regression model. The non-hypothesis is always going to support a simple model, while the alternative is going to support a complicated model. Okay. Now, as you can see, we're going to look at the p-value associated with this test. The p-value associated with this test, you can see, is 0.0161. You're going to compare 0.0161 with a level of significance is 0.05. And what is going to be the conclusion now when the p-value is less than a given level of significance? You're actually going to reject the non hypothesis. Rejecting the non hypothesis here means your conclusion will be in favor of the alternative. Does that make sense to everyone? That makes sense, right? Okay. So that is how it's very, very simple. Okay. Now I want to go. Now I want to define a new. Okay, go ahead. Okay. Yeah, the log like is, when you want to, the other time when I was okay, you say G equal -2 log L0, right? So that log L0 and log L1 is what is being displayed here. Do you see log like? Okay, the -167.7 is for the HO is the log L0. Okay, y -16575.8 is for the log L1. Does that make sense? Okay, so that makes sense, right? As no, the G, that is not G. The G is, look at the chi-squared, the one of 5.7915. Okay, so when you subtract that and you multiply by 2, if you want to go back to the G, look at the G now. This is the G. -2 times that minus negative. It's more or less subtract them, multiply them by 2 automatically. Automatically, you're basically going to have a chi of 5.7915. Okay, but you know what? just just go without. You don't need formula. Just do without. The moment you write the code, do you know what you're interested in? You are interested in the p-value associated, because you know why? That is going to follow a chi-square. Does somebody want to ask a question? Oh, okay. Okay, now I want to go into another one. We want to compare other two different modules. In the simple model here, we got a study time and maybe the midterm one grade. Don't forget, when we look at the effect of study time, midterm one grade on the final grade. The final grade is categorical. It has two levels. And there are another module, complicated one, is we got a study time. And then the first the midterm one grade is the midterm two grade. Take a look at that. So that is complicated. We're also going to do the same. LR test, like I said, the next step is simple. Put simple, comma complicated. Okay, and you're actually having this as a result. Take a look at that. Okay, so having this as a result, you take a look at the p-value now. Okay, the p-value here is less than any reasonable level of significance, and that will automatically lead to what I call rejection of the non-hypothesis, and that will support, the complicated model what we're trying to tell the world. If I basically want to predict the final grade that is categorical, I need a study time. I need a midterm one grade and midterm two grade. Okay, so another thing I want to talk about is what are the steps involved in analysis of logistic regression model. Okay, I need you to pay attention to this now. Okay, so I'm going to be using example from bank. I'm going to be using bank data example. Okay, the bank data example contain like 10,000 individuals. The bank, when you open accounts in the bank, of course, the bank asks your information, right? Information about whether you are a student or not, your gender, and so on, like that. And there's something that we call default. okay, where indicate whether or not an individual defaulted. Okay, maybe you get a loan. Okay, some pay back, some do not pay back. Okay, when you don't pay back, then you have defaulted. Okay, now, and student, a variable that indicate whether or not an individual is a student. Okay, and balance, which is going to be the average balance carried by an individual. Okay, and income, then income of individual, because I know when you basically approach a bank, uh, you know, to open an account, they're actually going to collect this information, from you. Now, let's say what we want to do now. This particular bank, they have information about 10,000 individuals, their customers, and they basically want to identify whether a particular customer will default or not. Okay. Now, step one, we need to first load your data set. Okay. If you want to have access to that data set, you need to install ISLR package. You install that, you load that. Okay, then you do the summary. Let's do the summary of the data. The summary of the data. Okay, if you take a look at the fault, okay, 9,667 customers have not defaulted before in this bank, while 333 have defaulted. We're actually using the information available to this bank. And a good number of customers in this bank are not students. Okay, there you can say the balance, the minimum, somebody minimum balance zero, the maximum balance 2,600, and take a look at that. They take a look at the income, and of course we got 10,000 customers in this bank. Now, because we basically want to pursue prediction, okay, the better way when you have a lot of data set like that, and you basically your intention is to make a prediction. Okay, we're actually going to split our data set. We're going to split our data set into training and into test sets. Okay, so we're going to set seed, where all of us, if we put the same number, we actually the when we are actually splitting our data, because it's something that we're going to be doing at random, we're actually going to get the same set of data. That's what it means by setting seed, okay, for reproducibility. Now, a good number of the data set is going to be committed to training, and why a few of that will be committed to testing. Okay, now this is a coding now. What I'm trying to tell the world now is 70% of this data set will be committed to training, while 30% will be committed to testing. Okay, this is the code. And after that, I'm going to go to step three. In step three, now I want to fit my model. You know what? The idea behind splitting your data into training and testing, that will give you an opportunity to be able to tell about the performance of your model to unseen data. Does that make sense? That is the idea behind splitting your data. Let me tell you this: in statistical analysis, when your interest is on looking at the effect only, you don't need to split your data. You need the whole data set. But if you want to make a prediction, okay, if you are actually pursuing what I call a predictive goal, okay, uh, and you have a lot of data set, it is advisable that you split your data set so that you're actually going to learn the model from the training data, and you're basically going to test your model using the text data. Okay, now take a look at that. Now model GLM, the fault is the response variable, either you're going to default or not. Okay, we are looking at the independent variable, like it is whether you are a student or not, your balance of the account, and your income, family equal to binomial, because of the fact that the response variable is categorical, and our data equal to train. We're using the train data now. We're not using all the data set. We're using 70% of the entire data set. We're not using all of that. Then let's look at the summary. This is the summary. Take a look at that. Can you see the summary? Okay. Now, if you take a look at this summary now, okay, it's trying to tell me, uh, student, whether you are a student or not, and where your income does not is not significant, right? The only one that is significant here is the balance on the account, okay, as regard to default. But you know what? This is not what we're going to use. This is just a this output is based on the training data, okay? It's based on the training data. We're basically going to look at the the interpretation of estimate here. Don't forget, I call them log odd estimate. You remember? The estimate, they're going to be called log odd estimate. In case you now want to be interpreting them, okay, take a look at the interpretation. The coefficient in the output indicate the average change in the log odd of the 14. You have to say log odd of the 14. For example, a unit increase in balance is associated with an increase of 0.005. Take a look at that. The 0.005988059 that you see in the balance is what we're interpreting now. Okay, that's what we're interpreting now. Take a look at that. Okay, now another thing we're going to do is assessing the mode of fit. We're also going to consider what we call, in linear regression, we use R square, right? Well, what we call the coefficient of determination. But here in logistic regression, we basically going to use McFadden's R squared. Okay, the McFadden R squared, we believe that which ranges from 0 to just under 1. So values close to 0 indicate that the model has no predictive power. Okay, and in practice value over is 0.4, okay, indicates that the model fit the data very well. If I basically want to assess my logistic regression model, I can actually use the idea of McFadden's R squared, and anything from 0 0.4 and above is okay. Okay, now if you want to do that, I can install a package called PSCL. Okay, then I'm gonna get the McFadden. Oh my god, the McFadden R squared. Now we got now is 0.47288807, which is trying to indicate that the model fit the data very well and has high predictive power. Now, another thing that we do in machine learning, okay, in machine learning, because this actually fall under machine learning now, okay, we can look at the variable importance, the predictor variables that we have. How important are they? When I install a package called Carrot and I load it, I'm just going to do var imp. Okay, you know what it's telling me now? Okay, which one has the highest number is balance. The balance on your account is the most significant variable that contributes to whether you're going to default or not. And if you go back to the output in the statistical output, you're basically going to see that that balance is even significant. Can you see that now? It's an agreement, right? So take a look at all of that. Okay, so the next thing I'm actually going to do now is we can also test one of the assumptions of logistic regression, particularly when you have more than one predictor variable, is that there must be absence of multicollinearity. We also need to investigate that. Of course, you know how what we did when we're working with the linear regression, we look at the VIF, right? The VIF, if anyone has a VIF greater than 5, that's problematic. But what can you see now? All of them are less than 5 for student, balance, income, which means there is no problem of multicollinearity. Okay, now the next thing now, let us now use our model to make prediction. We want to use our model now, okay, to make prediction. Okay, let's say somebody has a balance of 1,400 in his account, an income of 2,000, okay, and we can actually predict the probability that that person is going to default, whether it's a student or not. That is what we just did here. Look at that. Okay. Yes, student. Yes, for student it is 0.02732,106. No student is 0.04. Okay, who has more probability of defaulting? Somebody who have more probability of defaulting is somebody that is not a student. You see that now? That's what that guy is saying. Now, the other time I was talking about splitting our data, and we've used the training data, right? We now want to use a test, when you want to do model diagnostics. How well is my model? Apart from using the McFadden R squared, we can actually test our test data on the model, because we already know the status of our test data, and we basically want to see what the model is going to say. This is a code. Take a look at all of that, and we're going to have an optimal value. Okay, then we're going to make use of the optimal value, and from there we're going to create a confusion matrix. Now the confusion matrix, the 0 1 here is what happened in reality, and a 0 here is what the model predicts. Okay, 0 means the person is not going to default. The customer is not going to default. 1 means the customer will default. What is the meaning of 2,912? The 2,912, they did not default. Our model said they did not. That's a correct decision, right? Okay. Now, 39 defaulted, and our model said yes. What about 64 and 21? The 64 and 21 are what I call misclassification. That is the error by the model. Does that make sense? So this is a confusion matrix that will actually tell us, if you really want to figure out what is the accuracy, okay, and so on like that, take a look at that. Sensitivity, okay, specificity. You can calculate the total misclassification error. The classification error here, misclassification error is very, very small. What do we mean by sensitivity? The sensitivity is the ability of a model to detect. If some customers are going to default, okay, what is the probability that the model will detect that? That's what we call sensitivity. We also use this sensitivity in medical diagnosis. Somebody have a disease. Okay, what is the probability that the machine that you are using will detect that? Here now, a customer is going to default in a bank. What is the probability that our model will actually detect that? Okay, then for the specificity is the customer is not going to default. What is the probability that our model will detect that is not going to default? That's very high. And let me tell you this, sensitivity and specificity cannot be high at the same time. One will go up, the other one will come down. Does that make sense? And that is why you're seeing it that way. But the fact that the specificity is very, very high like that, there's no problem. And that is a total misclassification error. Let me tell you this, when we are dealing with a classification, because our model is not perfect, there's always going to be an error due to misclassification. Does that make sense? And what we're trying to do is to minimize that. Oh my God, that is going to be the end of my lecture today. Is there anyone who want to ask question before I go? Okay, there's going to be a public holiday tomorrow, and the lecture material for tomorrow, I'm actually going to make recording, and I'm going to share with you the lecture that we are supposed to do tomorrow, because the summer semester is very, very short, and I don't want you to miss out on some things that you should know. So because of that, the material for tomorrow, of course, the material for the rest of the week and even next week have already been uploaded for you to see. But the lecture material for tomorrow, I'm actually going to make the recording tonight, and I'm going to share the recording on Canvas, even though we're not going to be around in class tomorrow to mark the anniversary, the independence anniversary. Okay, but you can maybe anytime you can just go to India and listen to tomorrow's lecture. I wish everyone happy independent anniversary. Make sure you stay safe and have a lovely day. Bye for now,
Thank you.
everyone.
Beautiful one.
You
Bye bye.
welcome. You welcome.